Exclusively, the generation of electricity is in the form of alternating voltage or current, and in its transmission the energy losses are the minimum. The available alternating voltage is unsuitable for certain electric and electronic circuits, and for their functioning we require a direct power source. A solution for this requirement is to convert the alternating voltage or current to direct voltage or current. The process by which an alternating voltage or current is converted into direct voltage or current is called rectification. The electrical device which converts the alternating voltage or current to a direct voltage or current is called a rectifier. Whenever we apply an alternating voltage or current to a rectifier, the rectifier offers negligible resistance to the flow of current in one direction, while it offers extremely high resistance to the flow of current in the reverse direction. The valve-like action of the device allows a unidirectional flow of current through it. That is, an AC or the alternating current is converted into an unidirectional direct current. We know that a PN junction diode offers very little resistance when it is forward biased, and it offers very large resistance when it is reverse biased. This is a PN junction diode. It's a P and the N. So, a PN junction diode is eligible for being used as a rectifier. Rectifiers contains one or more diodes, semiconductor diodes. The rectifiers can be broadly classified into a half wave rectifier, and a full wave rectifier. So, we will be dealing with the half wave rectifier in this video. The circuit diagram of a half wave rectifier is as shown in figure. It consists of an alternating source, a step down transformer, a semiconductor diode, and a load resistance RL. An alternating supply voltage is fed to the primary of the transformer P1, P2, and the step down output voltage across the secondary S1, S2 is fed to the semiconductor diode D, which is connected in series with a load resistance RL. The applied alternating voltage alters the polarity at the ends S1 and S2 of the secondary coil. That is, during the positive half cycle, suppose if S1 is positive with respect to S2, in the negative half cycle S1 will be negative with respect to S2. During the positive half cycle, S1 is positive with respect to S2, and the diode D is forward biased. It conducts through the load resistance RL for all instantaneous voltage greater than the knee voltage. If this semiconductor is made up of silicon, its knee voltage is 0.7 volt. If it is made of germanium, its knee voltage is 0.3 volt. So, whenever it is forward biased, and if the instantaneous voltage is great, if it is made up of silica, if it is greater than 0.7 volt, it will conduct through the load resistance. The voltage across the load resistance has the same shape as that of the input alternating voltage. During the negative half cycle, S1 will be negative with respect to S2, and the diode will be reverse biased, and therefore it does not conduct. Therefore, there is no current across the load resistance RL. The net result is that only the positive half cycles of the alternating voltage appears across the load resistance RL. It is evident that the output is not a steady DC but a pulsating DC with a frequency equal to that of the input frequency. And now if we measure the output across the RL, we will get an average value of the DC. Since the circuit uses only one half of the alternating voltage, this circuit is called the half wave rectifier. Let us look into some of the performance related parameters of a half wave rectifier. The first one is the average of the DC value of the output voltage over a cycle. Suppose that the input voltage V is equal to Vm sin theta. We want to find the average value of the output voltage. Let us look into the waveform of the output voltage of a half wave rectifier. We can write that the Vm is equal to Vm sin theta in the range 0 to pi, and its value of voltage V is equal to 0 in the range pi to 2 pi. So let us take the average or the DC value of the output. It is taken as VDC is equal to 1 by 2 pi integral 0 to 2 pi V d theta. Substituting the value of V from this equation here, we get VDC is equal to 1 by 2 pi integral 0 to 2 pi Vm sin theta d theta. Vm is equal to, we are splitting from the range 0 to pi to pi to 2 pi. So Vm by 2 pi into integral 0 to 2 pi sin theta d theta plus integral 0 to 2 pi 0 d theta. So integrating this integral 0 to 2 pi sin theta, we get minus cos theta from 0 to pi. Substituting the values of this, you get VDC is equal to Vm by pi, or VDC is equal to Vm by pi. So VDC is equal to 0. Substituting the value of pi, you get 0.318 Vm. This means that the output DC voltage is about 31.8% of the maximum input voltage. Similarly, we can get the value of IDC as equal to Im by pi, which is equal to 0.318 Im, where Im is a maximum input current. The second parameter is the root mean square value of the output voltage. Vrms is equal to 1 by 2 pi into integral 0 to 2 pi V square d theta the whole raised to half, which is equal to 1 by 2 pi integral 0 to 2 pi. Substitute the value of V as Vm sin theta, so it becomes Vm square sin square theta d theta whole raised to half. So take out Vm square outside, so it is Vm square by 2 pi into it is split in two regions, 0 to 2 pi and pi to 2 pi. So it is integral 0 to 2 pi sin square theta d theta plus integral pi to 2 pi 0 d theta whole raised to half. This term goes to 0, and integrating this, you get the value as pi by 2. So this is Vm square by 2 pi into pi by 2 the whole raised to half. Pi cancel out, you get the value Vm square by 4 the whole raised to half. You get the answer as Vrms equals Vm by 2. Similarly, we can also calculate the root mean square value of the output current, that is Irms is equal to Im by 2. Efficiency of the rectifier, it is given by the term eta. Eta is equal to the DC output power divided by the AC input power. The output is taken across the resistance RL. So the output, the DC output power is I square DC into RL. The input always sees the diode as well as the load resistance RL. So AC input power is I square RMS into RF plus RL, where RF is the forward resistance of the diode. Substituting the value of IDC, which is Im by pi, and the value of Irms, which is Im by 2, we get the equation eta is equal to Im by pi the whole square into RL divided by Im by 2 the whole square into RF plus RL, which is equal to, substituting the values, you get the value to be equal to 0.406 divided by 1 plus RF by RL. In general, we know that the forward resistance of the diode is very small compared to the load resistance RL. Therefore, the efficiency of a half wave rectifier will be approximately equal to 0.406 or 40.6%. This means that in a half wave rectifier, only 40.6% of the AC input power is converted to the DC output power. The output voltage of a rectifier consists of two components, an AC component and a DC component. The AC component is called the ripple, which is an undesirable component in the output. The smaller the ripple, the more effective the rectifier is. The term ripple factor estimates the amount of ripple component in the output. It is defined as the ripple factor is defined as gamma is equal to the RMS value of AC component of the output voltage divided by the DC value of the output voltage, or it is the VAC, the output voltage divided the AC voltage divided by the DC voltage. We know that VRMS is equal to the square root of VDC square plus VAC square, or from this we can take VAC as equal to the square root of VRMS square minus VDC square. Substituting the value of VAC in this equation, we get gamma is equal to VRMS square minus VDC square whole raised to half divided by VDC, or V square RMS by V square DC VDC square minus 1 whole raised to half. Substituting the value of VRMS as Vm by 2 and VDC as Vm by pi, you get the relation gamma is equal to Vm by 2 the whole square divided by Vm by pi the whole square minus 1 whole raised to half. Vm cancel out, and substituting the value of rest all, you get the value of gamma to be equal to 1.21, which means that VAC divided by VDC is equal to 1.21. The result shows that in a half wave rectifier, the AC component is greater than the DC component. We can reduce ripple in a half wave rectifier by adding filter circuits into it. For practical purpose, the half wave rectifier is not desirable.